Welcome to you all in my YouTube channel Express Mathematics. In today's video, I am going to explain you about linear combination of vectors. A vector R is said to be a linear combination of a set of vectors A, B, C dot up to vector V if R can be expressed as vector R equals to xa vector plus yb vector plus zc vector plus dot plus tv vector where x y z dot t are the scalars. Okay, so a vector R is said to be a linear combination of a set of vectors a, b, c v vector if R can be expressed as R equals to xa vector plus yb vector plus zc vector plus t v vector where x, y, z t are the scalars. Okay, so if one vector can be expressed in this form, then vector R is said to be the linear combination of the given vectors a, b, c and up to vector b. Okay, this is the definition of the linear combination of the set of vectors. Example, if vector R equals to ai vector plus bj vector plus ck vector, then R is said to be a linear combination of vector I, vector j and vector k. Okay, this is the example of the linear combination. Okay, so here how it is called linear question arises. Okay, so here this x, y, z t are scalars, and when power of the variable is 1, then we say that the equation gives us the straight line. Okay, so here also x, y, z power is 1, so just to remember, okay, so we can call it as the linear combination. Okay, all right, now next that is the linearly dependent and independent vector. Okay, so before starting linearly dependent and independent vectors, so if you have not already subscribed my channel, please subscribe it right now so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about my coming videos. Okay, so now let's begin linearly dependent and independent vectors. Dependent and independent vectors. They are dependent and independent vectors. So in this same linear combination, okay, so this xa plus yb plus zc plus tv, this equals to 0 instead of r equal to 0, then here if x, y, z, t, they are scalars and all of them are not 0, then that is known as the linearly dependent. The vectors are said to be the linearly dependent. A, B, C, B are said to be linearly dependent. Okay, that definitions will write here. The system of vectors, vectors A, B, C dot 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 up to vector B is said to be linearly dependent if there exists a relation of the form xa plus yb vector plus zc vector plus dot 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 plus tv vector equals to 0. Okay, so in our linear combination vectors r equal to, we have written xa plus yb plus zc plus tv vector, and instead of r if we write 0, then we can also write this relation easily, where x, y, z da, 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 t are scalars such that at least one of them is not of them is not 0. Okay, the system of vectors a, b, c vector b is said to be linearly dependent if there exists a relation of the form xa vector plus yb vector plus zc vector plus plus tv vector equals to 0, where x, y, z t are scalars such that at least one of them is not 0. Okay, so this is the definition of the linearly dependent vector. Okay, this is the definition of the linearly dependent vector. So this is the definition of the linearly dependent vector. So we can easily define linearly dependent vector if we just remember the definition of the linear combination of the vector. So in linear combination of the vectors, here instead of r if we write 0, and if we just remember that x, y, z and then this t, these scalars, all of them are not 0, then these vectors a, b, c vector b, they are the linearly dependent vectors. Okay, they are known as the linearly dependent vectors. Okay, so if we remember one thing, then that will help us to remember the next thing. Okay, it's just like chain. Okay, so gradually if we read, then it will be quite easy for us. All right, now let's look at its example. Example, if vector r equals to xa vector plus yb vector plus zc vector then xa vector plus yb vector plus zc vector plus when it comes to other side then becomes minus 1 vector r equals to 0. So the set of vectors a, b, c and vector r, they are linearly dependent because here scalar this minus 1 is not equal to 0. Okay, even if this xyz 0, but here minus 1 is not equal to 0. So this set of vectors a, b, c vector r, they are linearly dependent. So a set of vectors a, b, c and r is linearly dependent. Okay, so here this set of vectors a, b, c and r, they are linearly dependent, right? So here in this linearly dependent case, so if x, y, z and then this scalar, another scalar also all will be 0, then there is freedom for a, b, c and vector r to have any value. Okay? So they will not depend upon each other, but here if x, y, z and this constant they all are not equal to 0 at the time, to make 0 they will depend upon each other, so the name is the linearly dependent. Okay, in that way also we can remember this one. And next, that is the linearly independent vectors. Okay, just opposite of linearly dependent vectors, we can define linearly independent vectors. Let's define linearly independent vectors. Linearly independent vectors. Independent vectors. A set of vectors. A set of vectors a, b, c to vector b is said to be linearly independent if in the relation xa vector plus yb vector plus zc vector plus plus tv vector equals to 0, all the scalars x, y, z t are 0. Okay, so here the name is the linearly independent. Okay, so here if all the scalars x, y, z and t, they are 0 and this sum is equals to 0, to make 0 then a, b, c and then vector b, they have no contribution because scalar will make them 0, so they can have any value, they have freedom. Okay, so they are linearly independent. Okay, in that way we can remember this definition. Okay, now look at the example of this. A pair of non-zero and non-collinear vectors A and vector B connected by the relation xa vector plus yb vector equals to 0 are linearly independent. Okay, they are linearly independent. Here in two-dimensional vectors also, in previous video we have discussed that if A and B are two non-zero and non-correlated vectors and x and y are scalars such that xa plus yb equal to 0, then x equal to 0 and y equals to 0. We had written that thing, and here both scalars are 0, then vector A and vector B, these are linearly independent vectors. Okay. All right. So now we have some notes. Another way of showing linearly independent vectors. Okay. The two vectors vector A equals to a1 a2 and vector B equals to b1 b2 will be linearly dependent or independent according as determinant of a1 a2 b1 b2 equals to 0 or not equals to 0. Okay, so here these vectors will be linearly dependent if determinant equals to 0 and linearly independent if determinant is not equal to 0. Okay, so here previously while defining linearly dependent vectors, what we had written that if the all scalars are not equal to 0, then the vectors are linearly dependent. Okay, then if all the scalars are 0, then the vectors are linearly independent. So here we have opposite relation, and it may be difficult for us to remember. Okay, so I will give you the one idea to remember. Here what happens is that if we make the linear combination here, ax plus by equals to 0. Okay, so here vector a times x plus vector b times y equals to 0, and in this, if this vector's determinant is 0, okay, at the time scalar can be non-zero. Okay, so if scalar non-zero, then they are any one of the scalar is non-zero, then these vectors a and b, they are linearly dependent. Okay, in this way you can remember this opposite relations of linearly dependent in the case of this determinant and in the case of scalars. Okay, here if vector 0, then scalar non-zero. So scalar non-zero means it is same as our previous definition. And scalar vector non-zero, then scalar can be 0, so linearly independent. So this will give us the idea of the equivalence between two type of processes to show linearly dependent and independent. All right, so now let's take space vectors. The three vectors vector A equals to a1, a2, a3, vector B equals to b1, b2, b3, and vector C equals to c1, c2, c3 will be linearly dependent or independent according as, okay, so according as here a1, a2, a3, b1, b2, b3, c1, c2, c3 equals to 0 or not equal to 0. So this determinant part equal to 0, then they are linearly dependent, and determinant not equal to 0, they are linearly independent. Okay, so in this case also the same process to remember. So if vectors 0 and any one of the scalars may be non-zero, so scalars non-zero, then the vectors are said to be linearly dependent according to our previous definition. And if vectors non-zero, then scalars, all scalars may be 0, so it is same as the definition of the independent vectors. Okay, so in that way we can establish equivalence between these two types of processes in our mind. All right, now look at here one example. If vector A equals to 3 minus 6 and vector B equals to minus 1, 2, okay, let's find out whether they are linearly dependent or independent. Then let's find out the determinant. 3 minus 6 is like a1, a2, and minus 1, 2 is like b1, b2. Minus 1, 2, determinant, let's find out. It is 6 minus minus is plus 6 equals to 0. Okay, therefore vector A and B are linearly dependent. Okay, so here I have already written that if a1, a2, b1, b2 determinant equals to 0, then the vectors are linearly dependent. So here also I have found a determinant equals to 0, so the given vectors are linearly dependent. Okay, in this way we can easily show whether the given vectors are linearly dependent or independent. I hope that you found this very helpful. Thank you for watching, and if you have not already subscribed my channel, please subscribe it right now so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about my coming videos. Thank you very much.